After every break, there's a whole different set of noises. I'm loving it. We're into Halloween now, which is great. Okay, that was your last break of the day, and we're about to hear from Katie. I think I mentioned earlier on that Katie spoke at the very first All Day Hey, which was nine long years ago. Haven't we grown? Look at us. Look what we've become. Look at us. It's amazing. I think this talk also is the culmination of many years of playing with APIs, experimenting, learning, iterating, evolving, and it's just we get to enjoy the fruits of that now. You may know Katie as the organizer of Frontier North, which is another wonderful event in the area. You're based in Sheffield,
yep.
Yeah, and just been building stuff for the web for a very long time. But enough. I just really want to see what fun is ahead of us. So please, for the last time today, a speaker to welcome. A huge round of applause, please, Katie Fenn.
There we go, get my slides up. Excellent, great. Hi, I'm Katie, and I'm a senior developer at the Financial Times. And a quick content warning before we start. This talk contains some really, really loud electronic music. I've seen Josh turning it up in the break. He's turned it right up to 11. Yeah, and as previously said, I'm a organizer of Frontier North. Our conference is on July the 10th. And tickets are just £75, and our social is at the National Video Game Museum. So please go and book some tickets and come and see us in July. So I really like Daft Punk, but you don't have to like Daft Punk to watch this talk, I promise. This talk isn't really about Daft Punk. It's more about the technology of electronic music, a whirlwind tour of the web audio and web MIDI APIs and what they're capable of, and a reflection on what the web is for. So just in case you don't know who Daft Punk are, they're a Grammy Award-winning electronic music duo from Paris. They're famous for dressing as robots while performing, and this is perhaps the image that most people are familiar with. But what many people don't know is that their career spans nearly 30 years. They were pioneers of the French house music scene, and this is the image that they selected of themselves for their first album in 1997. And early on in their career, they used synthesizers that were already old technology in the 90s, including the Roland TR-909 drum machine, which was released in 1983, and the Roland Juno 106 synthesizer, which was released in 1984. These machines could be found for under £100 second-hand because they were considered old hat. Yeah, they fetch 4 figures now, these things. But they did have a new technology that would change the way that electronic music was made forever. And that technology was MIDI. Yeah. This is what MIDI cables and ports look like. Nearly all synthesizers have them now. MIDI cables are very cheap and they're very easy to use. MIDI lets musicians synchronize different machines of different types and brands together, so you could prepare performances at home on your sequencer and then mix them into a live performance on your MIDI-enabled synthesizer or drum machine. Synthesizers were a common sight in prog bands in the 70s, and slowly they went from being a small part in a bigger band like Emerson, Lake and Palmer, to being the band. Bands like Kraftwerk, Pet Shop Boys, Erasure, Orbital, Chemical Brothers, Prodigy, and Daft Punk all used synthesizers to revolutionize the way that music was made. And now the Web Audio API and the Web MIDI API integrate analog synthesis and MIDI into the web. Now, these APIs are footnotes compared to our everyday work and the other APIs that we use, but they are very powerful and they're a lot of fun to play with. So let's explore these technologies by making a complete song. Let's make Daft Punk's 1997 single Around the World. For those in the audience, here's what it sounds like. There is going to be some really loud music in 3, 2, 1. All right, where do we start? Let's start with this. This is my Arturia Key Step Pro. I can't lift it up because it's taped down so it doesn't slip anywhere. That's what it looks like. This is a MIDI controller and a sequencer. It looks like a keyboard that you'd make music on in your bedroom in the 90s, but it's not. It's subtly different. This makes absolutely no sound of its own. It has no speakers. It's not capable of making any sound. This sends MIDI data to my computer. MIDI tells computers, synthesizers, drum machines which notes to play. MIDI data can even control lighting and visual effects on stage as well. And that really goes to show that MIDI is about message passing and absolutely nothing else. So let's hook this up to our browser using the Web MIDI API, and then we can see what MIDI data looks like. So this is where I start coding. Okay. So this is just normal DevTools. All my slides are in DevTools. That's what you're going to see today. And we're just going to load up a snippet. Right, so first of all, we are going to get the MIDI access from the navigator. The access object is like the gateway to the Web MIDI API. It controls everything that comes in and goes out, and it makes everything work. So let access equals await navigator dot request MIDI access. There we go. Then we're going to iterate through. Let's see, let devices of access.inputs.value. So we're going to iterate through all the devices, all the input devices that are connected. And if the device name equals KeyStep Pro, then we are going to do something. And what we're going to do is we're going to set device.onMIDI message equal to a callback. So this callback function is going to run every time we get a MIDI event, and we're going to use this callback to do things, to run some code. And we're going to pass in an object called message. Then what we're going to do is we're going to use document.querySelector. And we've got a nice little element in my slides set up so that we can take a look at what MIDI data looks like. And I'm going to set inner text equal to message.data. There we go. So just going to keep one eye on errors and we'll see what happens. I'm going to click play. Device is not defined. So let devices, I've already made a mistake. Fantastic. There we go. Let's see if we can see some MIDI data. There we go. Let's close DevTools so you can see, get a better look at this. So MIDI sends a lot of data, but the essential core is a set of 3 different values. The first value is the status byte, and it's often used to identify the control that's being pressed or interacted with. Some controls have different values based on their context. So it will be different if I press a key down, in which we get 153. If I lift the key up, then we get 137. The second is the data byte, which carries information such as the note that's being played. So if I press key down on low C, then we get 153. If I go up a semitone, then we get, no, sorry, it's the middle one. So 36, 37, 38, 40, and so on. And then additional parameters may follow, such as the velocity or the range of a knob. So if I push the key very slowly, then the last number will be very low, like 1. And if I push it very fast, then it will be very high. And if I move some of these knobs, then it will be the range of the knob. So it will start off very low and it will go up very high. You don't need any API documentation to understand these values. This is one of the great things about MIDI. It's designed to be learned intuitively. You expect these values, and providing that you perform the same action in the same way on this sequencer, then you will always get the same values on your computer. Counterintuitively, this makes it much easier to use. If you've used a digital audio workstation such as Logic Pro or Ableton, you might have seen that if you want to use something like this to automate changing a parameter or changing volume of something using one of these knobs, you put it into a special learning mode and you say, I want to change this parameter, learn this control, and then you move the control and it will learn it intuitively. And you write your code in the same way. That's one of the things that makes MIDI absolutely brilliant. So that's MIDI. So now that we know how to tell the computer to make noise, we need to figure out how to make the computer make that noise. And this is what the Web Audio API is for. The workflow for the Web Audio API works by connecting different nodes together. And you're going to see me write a lot of code like this, but this is what it boils down to. So you take an input, a source of a noise, you shape it using different effects, and then you send it to a destination which by default is the audio output selected in your operating system. And this workflow models the way that a real hardware synthesizer does, where you patch an oscillator into an output in order to make a noise. So we'll start with oscillators. Oscillators create an electronic signal that make a noise when you connect them to a loudspeaker. So I've hooked up my real synthesizer to an oscilloscope so you can see the shape of the sound that they make. So this is a sine wave. It's nice and soft. Sawtooth wave is very sharp. And a square wave is kind of mix of the two. This is a pulse wave. You can change the pulse width to make it softer or sharper. And you can play higher frequencies to play higher notes. Or lower frequencies to make lower notes. And when you put all of these techniques together, you have the foundation of all electronic music. So let's see if we can make an oscillator. There we go. Going back to DevTools, going back to the sources panel, and we'll go to oscillators. Right, so just like the Web MIDI API, we have a gateway object, and we're going to call it context equals new audio context. There we go. And what we're going to do is we're going to create the first of our nodes. If you remember the diagram where I had like different nodes connected together, we're going to create our first one. That's going to be called oscillator equals new oscillator node. The first thing that you do when you create a web audio node is that you need to pass in the context, and that helps. That coordinates all the different nodes together that you're going to be making, and it's always the first argument that gets passed in. The next object is an options object, and there's lots of different options for each different kinds of nodes, and one of the things that we can set is the type of wave that we want, and I want a sawtooth wave that we saw just a minute ago. What have I missed? So, delete one on line 7. Fantastic. Thank you so much. So, oscillators, by default, start making a noise and they don't shut up until you refresh the page. And that's not what we want. As you know, when you use a synthesizer, when you push a key down, you hear a noise. When you lift the key up, then you don't hear a noise. So what we need is a gate of some kind. And this is a kind of electronic circuit that you find in real synthesizers, where when you push a key down, you hear a noise, and when you lift it up, you don't hear one. So we're going to create a gate. We're going to use a gain node for this. So new gain node. We're going to pass in the context, and we're going to set the gain by default to 0 because we don't want to hear it initially. It will increase the gain later on that signal through. So next we're going to connect the oscillator. And we're going to connect that through to the gain node, and then we're going to connect the gain node to the context.destination. And the destination by default is the default sound output configured in your operating system. So that might be your loudspeakers, that might be your headphones, and for us today it's the PA in this cinema. And then I'm going to start the oscillator. Oscillator, start, and that's going to start that oscillator oscillating. So next, what we need to do is we need to control what's going to happen to the oscillator in the gain node when we actually push a key down. So we need to, first of all, set the frequency to the desired note that we want to play. So we're going to set oscillator.frequency.value equal to, so I've got a nice little handy helper function that I created earlier. It takes in a MIDI number, it takes in a number supplied from MIDI, and it turns it into a frequency in hertz. So I'm going to use MIDI to frequency. I'm going to pass in MIDI data.input. And then next what we need to do is we need to open that gate when I push a key down. So on key down, I'm going to set gain.gain.linear ramp to value at time. And we're going to set it to 1. And then I've got a nice little helper function up here, which is the current time plus 0.005 seconds. And then on key up, we're going to do the opposite and set it to 0. And let's see if I made any more mistakes. So I'm going to push play on that, and hopefully we will hear a sound. Oh, that's really loud. Sorry about that. Okay, so you can hear that. You can, like, I've pushed the key down, and it's making sound. So we'll move on to something else. There'll be more loud sounds in a minute. Okay. Right. So, bass lines. So let's see if we can make something that's recognizable from the song. Let's take that really loud sound and turn it into a bass line. So what we need is a filter. And filters are used to quieten, remove, and accentuate certain frequencies of sound. And they're often used in electronic music bass lines. This video shows me patching an oscillator into a filter and then into the output of my synthesizer. So I'm going to take the output, plug it into the input of the filter, then plug the output of a filter into there, and we're going to make it a sound again. So the filter is filtering out the higher frequencies of that sound, which makes it sound nice and thick and creamy. So let's see if we can do that. Let's see if we can make a filter. Let's go back to DevTools. Right. Bass filter. Right, so this is a very, very, very similar demo to what we had earlier. We've got an oscillator, we've got a gain node, and now what we're going to do is going to create a filter. So let filter equals new biquad filter node. I think biquad filter is just a fancy name for a filter that you can configure in 2 sets of 2 places, and that's why it's called biquad filter node. And we're going to pass in the context, and we're going to set the frequency of the, that's spelled wrong. We're going to set the frequency of the frequency of the noise that we want to cut out to above 144 hertz. So we can set that to 144, and we are going to run that. And let's see if we can have a nice thick bass line. So, okay, let's see. What did you see?
The red box at the top, but no, you don't want to, yeah, you ignore us.
Okay. Okay, we'll see if it makes a noise. Ready? 3, 2, 1. So that's a nice soft, that's a softer sound. So if I turn it down an octave. Whoops. Okay. Yeah, there we go. There we go. So we have our bass line. Excellent. What's next? Let's see if we can make a lead. Let's see if we can make the lead melody. So the next thing that we need to learn about is low frequency oscillators. Low frequency oscillators, or LFOs, are designed to make a noise. Not designed to make a noise, but they're designed to modulate and automate parameters of other sounds. So this video shows me patching an LFO into the pitch of an oscillator for an accentuated tremolo bass drop effect. And I'm going to change the frequency of the LFO, so you'll be able to hear the pitch going up and down faster and faster and then slower. So we're going to have more loud noise in just a second. So I'm going to patch that LFO into the pitch of the oscillator. Then I'm going to turn up the frequency. There we go. So let's see if we can create a low frequency oscillator. Right, here we go. Back to DevTools. Let's see, lead LFO. Cool. So we are going to create a low frequency oscillator node. We're going to make it a type of sign, so let LFO equals new oscillator node. The great thing about LFOs in the Web Audio API is that they're just oscillator nodes with low frequencies. You can reuse them. You don't need a special LFO component inside your synthesizer. It is literally just an oscillator node with a low frequency. So we're going to set the frequency to 5 Hertz. We want to make it nice and slow. By default, oscillators oscillate between 0 and 1 values, and we want to use this oscillator to oscillate the frequency, the frequency cutoff of the filter. And if I only oscillate the frequency cutoff by 1 Hertz, you are not going to be able to hear it. So we need to amplify the oscillator, and we want to amplify it by about 5,000 Hertz so you'll be able to hear it. So we're going to create an object called LFO gain. And that's going to be a gain node. I'm going to pass in the context. And we want to set the gain to 5,000. And then we're going to connect the LFO to LFO gain. And then we're going to connect the LFO gain to the filter's frequency property. And we're going to start the oscillator, LFO.start. There we go. Let's see if it's working. And we're going to have some more loud noise in 3, 2, 1. So you should be able to hear that filter opening and closing about 5 times a second. And in fact, what I can do is I can just play around with my code, and I can make it 20 times a second if I want, and you should be able to hear it get faster. It's automating. I could not change any of the parameters by 20 times a second with my bare hands if I wanted to. So LFOs are automating aspects of other bits of my code. Whoops, wrong. There we go. Okay. So let's see if we can put this all together and make a complete piece of music. So let's load this up, inspect, sources, complete. And what I'm going to do is I'm going to leave the console open, so you should be able to see all the MIDI data coming through. Okay, here we go. So make sure I'm on project 4, okay, and music in 3, 2, 1. Ooh, okay, hang on, I need to press play. Let's do that, let's do that. Okay, 3, 2, 1. Right, so that's the Web Audio API. How would I sum it up? It requires domain knowledge to get started. So it is designed a little bit to, to be useful if you know how a hardware synthesizer works. But with that said, it's not hard to take your first steps. Easy things are easy-ish, and hard things are possible. I think the really difficult thing for a beginner is to know which is which. It's also not a digital audio workstation like Logic Pro or Ableton. You won't have the same production tools, mixing, power and effects as they do when just starting out. It is, however, an excellent educational excellent in educational experimental roles. It's a lot of fun to play around with, and it's very well supported in Chrome, Edge, Safari and Firefox. The Web MIDI API, MIDI itself is well supported in musical hardware, but it's utterly let down by its lack of support in Safari. Apple have famously prevented any kind of support from being added to Safari on security grounds, bizarrely. But it is excellent for hobbyist development. If you want to play around with it, it's very easy to just connect a piece of technology like this, any kind of music production data, and start scripting it using a web browser, providing it's not Safari. So let's get to the final part of this talk. What does the web do best? Should we be thinking of integrating Web Audio API into our sites and playing Sandstorm whenever anyone clicks something? I know Dave would like that, I know Remy would like that, but no, I don't think so. Absolutely not. Is it a replacement for serious audio production tools? Nope, Ableton and Logic will give you a lot more power and control out of the box. But that doesn't mean that the Web Audio API and the Web MIDI API are worthless. There's a huge community of hobbyists and experimental musicians out there, including people like this. These are circuit benders. Circuit benders make electronic music using scrap, toys, broken synthesizers, games consoles, and if they can make music out of rubbish, you can bet that someone will make something cool with a web browser. What makes MIDI so great is that it's used by practically everyone, amateurs and professionals alike. I knew absolutely nothing about electronic music or playing with synthesizers before I started writing this talk. That is honestly true. So it really does go to show how useful an educational tool the Web MIDI API and the Web Audio API can be. The web should be the software platform of the amateur, the hobbyist, the auteurs doing something that nobody has ever conceived of before. The web's compatibility, its ubiquity, its accessibility and its approachability make it the ideal creative platform. And this is a call to Apple to find a way to support the Web MIDI API on iPads and iPhones. The web and MIDI belong together. This is Dave Smith. Dave was an engineer and founder of Sequential Circuits and the creator of a famous polyphonic synthesizer called the Prophet 5. Together with the president of Roland, Iketaro Kakahashi, they created MIDI. To this day, MIDI remains completely unlicensed. No fees have ever been collected for its creation. Whole industries and art forms exist because of MIDI, and it remains easy to use for beginners and experts alike. And if that sounds familiar to you, you'd be right. This is Tim Berners-Lee, creator of the World Wide Web. Since its creation, Tim Berners-Lee has not collected any fees for creating the World Wide Web. Free and open standards create wealth for us all. The web has changed our lives for the better. It's critical that the web remains open and free and endures as the software platform of the common good. MIDI and the web are naturally allied to each other and deserve to endure together. Thank you very much.
Fantastic. Katie, thank you so much for, well, an entertaining but also a really important and poignant message at the end. Thank you so much. Another round of applause, please, for Katie Fenn.